Good morning, students. Well, I guess we've officially moved into the winter time. I think last evening, before I went to sleep, I checked the temperature and it was 32 degrees, and that officially is freezing. So I guess we're in winter before winter actually hits. So if any of your friends and relatives in other states are saying that we don't know cold weather, well, we do get cold weather, maybe just not to that extent. But I will say this, humidity plays a big factor in how we feel cold or even heat for that matter, as you well know. In northern states where the humidity is extremely low, you don't feel the chill. I mean, it could be 15 degrees outside and the humidity is so low that you're not really aware of the chilling cold that we feel in Houston. With the humidity high and a cold snap coming through, we feel it a lot more. So the reason I know this a little bit more is because when I visit relatives in Montana, they have that dry cold. And you do have to, however, be careful. You know, it can play tricks on your mind. So next time a friend or relative says that we don't know cold, we really do. But we do appreciate our warm weather. Okay, so next week I will post an announcement about our final exam. We've got another quiz and homework due, and then of course I'll give you another nice window of time to complete your final exam and hopefully provide flexibility as I have in the past. I know you'll have plenty of items to take care of in week 16. So I don't want to change how I'm going to set up that format. And of course, the testing will be the same. There'll be the WebAssign portion and the test work portion. And I think that gives me a better opportunity to see what you're doing. And as you've noticed in many cases, the testing with the two separate portions actually helps you to put forth what you're doing as far as your quality of written mathematics. So I'm very pleased that when I look at your work, I see some really good efforts, and that's really key to STEM education. As you work into your professional careers, it's important to be able to communicate effectively, you know, as opposed to speaking as well as the written, because there'll be times I'm sure when you will do presentations for your colleagues that you will want to be enhanced with good mathematics. Now, what we want to do today and for the today's lecture and the lecture on Thursday are cover the final two topics, one on mathematical induction or the principle of induction, and then of course the more general binomial theorem for larger positive integers. Just remember when you get to calculus 2, you will study the binomial theorem for any power, and that will be a little bit more complicated, but certainly very useful and give you plenty of ideas as to how your calculator works. So let's go ahead and look at induction. I want to start out with a simple example. So I want to share my screen. Now, lots of times students will say, well, why do I need, you know, anything past trig and conic sections? You know, we talked about the geometric sequence and the arithmetic sequence. Isn't that enough? And so what we want to be able to do is think a little bit more abstractly, because there are times when abstraction helps us out quite a bit. We found that to be the case in trig. And of course, we found that to be the case with the general equations for the conics. Because if we don't take the definition and work in the abstract, we can't develop a nice clean formula. And then once we have that formula, we have a pattern to recognize, just like a quadratic. Uh, we, we can only move forward in math if we understand the objects that are placed in front of us. And so it's important to develop new patterns. So in this particular section, 12.5, we're going to call this the principle of mathematical induction. Principle of mathematical induction. Now, before we actually state this, I just want to do a simple example. You can think that induction is a way to prove logical statements about natural numbers. But I want us to look at a formula that we've already considered in this class, which would be the sum of the first n integers. This is a partial sum. So I'll just say before we state this, consider the following partial sum. Now, like I say, induction is very powerful, but it is a verification type proof, whereas sometimes students appreciate algebraic, but for the purist, induction is a necessity. So we had this partial sum here. That is, if we added the first n natural numbers, I equal 1, we can use any index variable we like. And so if we added all of these, I mean, if we wrote it out, this is a compact form. We have an index variable I, and we're just adding I as the index variable changes from 1 to n. So this is 1 plus 2 plus 3, etc. to n. Now, we had a formula for that. I actually gave you the formula, but let's just consider, for instance, first, we might say, okay, this is really a logical statement about natural numbers. And we could call this, and this is the notation in your text, we could call this P of n, where this denotes a logical statement about natural numbers. So we might think, how could we come up with an actual formula here? So now I'm going to finish the statement and say that, remember, Professor Ron said this actually equals n times n plus 1 over 2. So I won't put the dot here and just go ahead and give you the punchline. So the logical statement about natural numbers would be that if you add the first n counting numbers, the partial sum formula, like we have for arithmetic, which of course we use this, and then geometric as examples in the past, would be this. And so you might think, okay, well, how could we go about showing that this was true? Well, let me give you one method that we call algebraic. So this would just be simple proof. And it involves a little trick. This actual proof is attributed to Carl Friedrich Gauss. That like I say, math history, maybe it's revisionist history, but he is credited with having determined this as a boy, as a youngster. So I don't know, that may have just been passed down and developed over the years. But the idea is that if you notice here, there's a certain symmetry that we have because the powers are all 1. So let's just note the following. So we're going to add this in this order. And I'm going to put an extra copy here. I'm just going to say n minus 1 plus n. Now what I'm going to do, and this was the pattern that was noticed. Unfortunately, this doesn't work for any of the others, and that's too bad. We can think of reversing this sum. You may have seen this before. We can think of reversing the sum, starting with n and descending to 1. So we could have n plus n minus 1. And of course, I'll go ahead and do the plus n minus 2 here, the term right before this one. And then of course, with the last two, we'll put a 2 here and then a 1. So the idea is that if we think of these two equations, we might think, okay, well, can we simplify these? What would happen if we actually added these two finite sums? Now, and the reason being is that we basically reorganized things, we've commuted things, we've moved them around, and then we reassociate. So this particular setup here makes that very easy. So I'm writing it in a very simple way. So here's what we're going to do. We've commuted everything by writing it in reverse order, and now we're just going to add pairwise. Okay, so let's add pairwise. So we'll get 1 plus n plus, just vertically here, 2 plus n minus 1 plus 3 plus n minus 2. And we'll keep going. We'll get n minus 1 plus 2 plus n plus 1. Okay? So again, using the axioms of the real number system, we commute and then we reassociate. So we add in any order we like, we group however we like. So here I've written it in a way so you can see that. Otherwise it might, we would lose a little bit of the idea that Professor Ron is trying to communicate here. Now, when we look at this, we notice a pattern emerging. So this is this, but this is also equal to, let's just write the n first. And then of course, 2 minus 1, that's just a 1. And then of course, 3 minus 2, that's just a 1. So we're getting, of course, this is starting to look inductive. 2 minus a 1, that's a 1. And then of course, n plus 1 is just n plus 1, just like we had here. So the idea is that when we look at this, we're thinking, okay, what did we actually do here? Okay, well, we took the partial sum and we added it to itself in a very creative way. Mathematics requires creativity, as you well know, and it's not always very obvious. So when I look at this here, I can simply say, okay, this is really 2 times the partial sum that we've written up here. And now we notice that we have n terms or n summands of n plus 1. That is, there are n of these objects and they're all the same. So this is going to be n objects of n plus 1. But then, of course, that gives us a formula for the partial sum if we divide by 2. So like I say, this is a very famous argument. You'll see it all over the place. So this would be a legitimate way to prove this. Now of course, the pure mathematicians, and a lot of my students call me that. I think I have a little bit more restraint, but pure is fine. You're thinking, okay, well, would this be good for any integer, n positive integer? I mean, what we've written here is abstract. We do 1 up to n, and n could really be any natural number. Maybe n is 10, maybe n is 20, or maybe it's a billion, maybe it's 500,000. And then everybody says, well, when we start doing that, is this still valid? And your intuition would say, sure, it's valid. And so what we would want to do, and this is where we have the axiom of or principle or axiom, if you want to call it, of mathematical induction. So the more pure mathematicians would say, well, it looks like you have a formula here. Okay, you've got a formula here. Algebraically, you've manipulated the partial sum, and you've come up with a formula, just like we did for the arithmetic sequence and the geometric sequence. you know, and we don't have an issue with that. But in some cases, it might be that you maybe came up with this formula uh, in another way. Maybe you were doing some research, and as you were checking your data, the same relationship was coming up over and over. And you said, you know, I think the sum of the first n counting numbers is this. Maybe you didn't do it this way. Maybe you didn't have an algebraic method that was a little bit more sophisticated like we had here. And then you thought to yourself, well, you know, how can I verify this? I think it's true. So that's when the pure mathematicians come in and say, well, you need to verify this by induction. And you're like, oh, well, isn't this good enough? Well, I'm here to say that in many instances, an algebraic rendering of this is sufficient. But when you get into discrete math topics and computer science and things, and even in number theory and combinatorics, induction is often the way that mathematicians and computer scientists like to verify, so to speak. So what I want to do is now state the principle of mathematical induction. So let's do that, and I'll get a separate sheet for that. So now you know, you think that formula I gave you is actually true, so I'm glad for that. So here's the principle. So principle of mathematical induction. So in this case, what we'll do is look at the following. So we're going to say, here's the notation I'll use. And I'll try to be true to the notation in WebAssign. Just remember, ladies and gentlemen, you can use any letters you want. And when you do a proof, you know, WebAssign will guide you, but you may think a little bit differently. But the idea is always there. So look at what you need to do and react in a way that maintains the formatting. So let P of n be a logical statement. I'm repeating myself, but it's good repetition. Logical statement about natural numbers, like the one we just did. I'm trying to give you a reason why this is valid. So many students say, well, what's induction? Well, so now you're kind of thinking, well, this is going to be a verification method. And what we're going to do is, for now, just to make this make sense, we're going to let S be all the natural numbers. So S will be all the natural numbers such that P of n is true. So for instance, you would say that 1 was in S if P of 1 were true. You would say 15 is in S if P of 15 is true. That is, we want S to be a subset of the natural numbers that would consist of all natural numbers for which this logical statement is true, okay? So, number one, suppose, in this case, 1 is an element of S. Like I said before, if 1 is an element of S, this would mean that P of 1 is true. Okay? And then 2, what I want to say here is for some K, and the WebAssign uses K, you could use N again, but they use K. K element of the natural numbers. P of K true implies P of K plus 1 is true. So you're thinking, well, that's kind of interesting. What are you saying here, Professor Ron? Well, when you look at this, we're just thinking in the abstract. We're saying for some natural number, some counting number, we're going to assume that P of k is true. And this will imply that P of k plus 1 is true. Like for instance, we're thinking in the abstract and you want to make it a little bit more cogent. So we think, okay, 23. We're going to assume P of 23 is true. And that will imply that for the next counting number, 24, that's also true. So in the abstract, we're thinking, what are we really thinking here? Okay, so if like it's true for 1, and then we apply this, it'd be true for 2. And then if it's true for 2, we apply this, then it's true for 3, because we just bump up to the next one. So we get P of 3 true. And then it's like, well, if P of 3 is true, we're back to here, and that will imply that P of 4 is true. And so we get this cascading effect. So the idea here is the induction process keeps you from having to check every natural number. So if we can verify like a starting point, maybe it starts with 1, maybe it starts with 3, who knows, it doesn't matter. But normally we will start with 1. And then we have this step 2 that says if we assume this and this implies this, then we should be in good shape. Now, what's the good shape going to mean? Before I give you the punchline, we're going to call this assumption here the induction hypothesis. Induction hypothesis. So a lot of students will say, oh, I proved it by induction, Professor Ron. And I'll say, did you use the hypothesis? Not really. And then I'll say, well, you may have proven it in some type of algebraic fashion, but you didn't use induction. So the induction process or principle requires that you show 1, and that if you assume this to be true, that you must show that this will imply this. And then cascading effect, that sometimes they call it the domino effect. Then S would be all natural numbers. That would say that now P of n is true for all natural numbers. And I can use like a universal quantifier that you may have seen that it looks like an upside down A for all. If you want to use that, you can. It's not required. Sometimes I use that in the SmartPen videos, but it's your choice if you want to use it. WebAssign doesn't always adopt this, at least in pre-cal, just to keep it more user-friendly. But if you look in other textbooks and if you take a logic course, you'll certainly see this symbol. Now, the idea here is that, just like I said before, with this process, we have a way of verifying. So what we have to do is we have to start out with the logical statement. That is, this statement here, we start out with this. You don't look at this so much as a derivation. The formula is already given, and then the principle of induction is a way of saying, verify this. This is what we're going to do, and then we'll know that this is actually valid. So that's the purest part that's coming in here that I keep mentioning, that it's like, well, we need to just, put this, that last nail in the coffin, so to speak. We need to make sure this is right, and so, like I say, the induction process is one of those verification axioms that puts your mind at ease. You're like, oh, I now believe it, kind of thing. Thinking about this proof and then thinking about a proof like this. Now, if you, and I thought about this yesterday, and this is actually fairly simple if we think about it. Why is this true? Why? I mean, it seems correct. And it would be hard to verify, because it's like, I started saying, well, if it's true for 1, it's true for 2. Then if it's true for 2, it's true for 3. Just keep applying this over and over. And then you say, okay, that's the proof. Well, it's not really a proof because it doesn't utilize anything except intuition. So you're thinking, well, how if we had to verify this or show that this process really did mean that S was all of N, how could we do it? Let me show you a simple technique here. And you're going to use this in calculus. Let's use a contradiction method, and then we'll do plenty of examples. So let's suppose that S is not all natural numbers. Let's just assume the opposite of what the induction principle says. Suppose we don't get everything. Suppose all the natural numbers don't work. Then, and I'll use this notation, N minus S is a subset of the natural numbers. So if this is not all of S, if we look at the set which subtracts from N all the elements of S, that's still a subset of N. Because if we assume the opposite of this, we're saying that S is not all natural numbers. Now, this is where we can be very clever, and induction requires us to be clever. So subsets of natural numbers are very special. They have a least element. When we think of the natural numbers, what's the least element of the natural numbers? 1, okay? If you have a subset of natural numbers, 5, 7, and 3, you can always find a least element. It's 3. That's called the well ordering principle, and that's an axiom. And that's really what this is saying. So we know here, we can say then N minus S has a least element. And if you want, just call it beta. I know it sounds like I'm doing trigonometry, like an angle. So this is a subset of the natural number, so it has a least element beta. Okay, the least element. Now, if you subtract 1 from beta, then you're not in this set anymore. You're going to be in S, right? Because if this is the least element, so therefore, B minus 1 must be in S. If that's the least element of this subset, if you go 1 less, you're out of the set. You've got to be in S now. Now you see what I'm doing. That's clever, isn't it? So you're thinking, well, we assume the opposite of this, but this is still valid up here. So we're thinking beta minus 1 is in S. Okay, so that's saying P of beta minus 1 is true. So we can apply this by 2 beta minus 1 plus 1, which equals beta, is an element of S. That is, P of beta is true, but we know that's a contradiction. You see, when we look at this and say, well, this beta is the least element of the complement of S in the natural numbers, saying it's not true. And then if this is the least element, we go down 1 and find an element that's not in here that must be in S. But then we apply 2, we get like, you know, the light is on, the light is off. That's a contradiction. We're saying here that P of beta is not true, and now we're saying it's true. So in this case, and write this in your notes, this just means P of beta not true, since beta is not in S. But here, this says P of beta is true. You can't have both of them. And that's what we call proof by contradiction. So when we assume that S was not all of N, we get something that's untenable. It's like the lights on and off at the same time, and that's a contradiction. So this is what we call the contradiction. And we're done. So this is our first proof by contradiction. Now, again, you will do some contradiction proofs. The idea is that as you get more and more sophisticated, this is actually a logical tautology. If you're trying to prove an implication, you assume that the conclusion is false, assuming that the hypothesis is still valid, and then you produce a contradiction. So this is basically saying that if you say P implies Q, this is equivalent to P and not Q implies the contradiction C. So again, some math professors don't like proof by contradiction, but this would be really hard to show if you didn't use contradiction. So if we can show that if we take the negation of the conclusion, which is the tilde Q, and apply that with the hypothesis and get the contradiction C, these are logically equivalent. So this is what you probably did in high school if you did geometry and you did a proof by contradiction. So this is proof by contradiction. So I didn't want you to think that I just made this up, that, well, Professor Ron is just giving us this mathematical induction journey and I think he made it up. Well, I didn't. The idea is that some things appear very obvious. It's like, you know, you get this domino effect from applying 2 over and over and over. And that's like, yeah, I get it. I can see why S is all natural numbers. But we need to put all doubt to rest. It's kind of like, you know, that you know, absence any doubt, we have this, you know, conclusion, so to speak, beyond a reasonable doubt, so to speak. We didn't become attorneys, but the thing is that if we look at this, we say, yeah, this is true. This is true. Because if we assume that it's not the case, we get something that doesn't make any sense. And so mathematics, we know, has to be consistent. So let's go back to our famous example and prove it by induction. And you'll forgive me for going out on a limb here. I thought about this yesterday and I said, if I don't give my students some reason to believe induction in a way that makes sense to them, then they're never going to understand it. And that's the issue with pre-calculus mathematics. If you don't get ideas that build your understanding, then you haven't improved any beyond college algebra. And that's where you get into trouble in calculus, when you've got to think on a higher level. So I'm trying to push you up to that higher level. So now let's do it. Okay, so we're going to prove this by induction. So here's our P of N. This will be, if we add the first N natural numbers, and we'll just use an I if you want. Well, we'll eventually use a K or whatever. I'll show you how we use the notation. Whatever notation you want to use is fine, ladies and gentlemen. I'll try to be consistent. So this will be 1 plus 2. I don't want you to have to write it out a million times. So this is really 1 plus 2 plus 3. This part you could leave out if you wanted. I'm just reminding you what this is. This actually equals N times N plus 1 divided by 2. That's the logical statement about natural numbers. And basically what we're seeing here is we're saying N is greater than or equal to 1, okay? And so now we want a proof by induction. So this is an induction proof. So remember, induction means that you have to bring to the table the hypothesis conclusion bit. You have to bring something that has to be verified. So you're not going to derive this like our haphazard way before, you're basically just going to say, we're going to verify this. So induction doesn't lead you the derivation path like we have here. It basically says, well, you've come up with this. Let's just do a complete verification. So I tell my students sometimes, if you can come up with an algebraic justification, we'll live with that. And sometimes you don't have any more time to do that. And so again, just remember that there may be times when induction will kind of save you from falling into the deep end, because if you try to prove it by some other method, you find it to be extremely difficult. So there's this give and take with induction. So let's go up here. Let's do what we have to do. For induction, we have to show that P of 1 is true. And you can use S if you want, but in WebAssign just uses the P's and all. So number 1, let N equal 1. So we'll just replace N with 1. That's not very difficult. P of 1, all the students like P of 1. They say, Professor Ron, I can do P of 1. I deserve all the points. Well, unfortunately, that's not the case. Okay, so P of 1, well, we start with 1 and we end with 1. So there's one term. So that equals 1. Okay, that wasn't very difficult. Now, that means question mark. If we replace N with 1, do we get 1? Well, let's just look. 1 times 1 plus 1 divided by 2. So that's 1 times 2, which is 2 over 2, which is 1. So indeed, this is true. So this implies P of 1 true. Now I may shorthand things. I could say is true, but we'll just keep it nice and quick and efficient. P of 1 is true. That is, if I replace N with 1, this formula is valid. And you're thinking, well, who cares about that? Who cares about that? But again, kids, we want the domino effect. We have to have some reason to move to step 2. For instance, if we can never get this to work for any number, then why would we ever want to go to step 2? That's some students will try to do an induction proof and they never achieved a P of 1 or a P of 2 or anything because the statement was invalid. So in order to get to step 2, you've got to do step 1. There's got to be some initial value in the natural numbers for which the statement is true. Otherwise, you don't ever need to move to step 2. Okay, it's kind of like doing the trig equations or whatever. As you work through things, or you work a quadratic equation or something, you know, you may not have to check certain things in a process, because, for instance, it'll say solve sine theta equals 5, and you're like, well, 5 is not in the range of sine theta. So you don't move to the next step because there's no step to do. The equation is invalid. It's undefined. So think about that way. So now what we want to do for step 2 is for some k, just say for k element of the natural numbers, P of k true. Now, some students say, well, okay, I'm just replacing N with K and I'm okay with that. Well, just write out what this means. And this is the notation that the author uses. You don't have to change to another variable. You could just write what's up there and stick with N. But Dr. Stewart switches to K, which is fine. It doesn't matter, your choice of letters. So in this case, this would just mean that we would get K times K plus 1 over 2. So changing the K is really nothing more than doing what we've done here. A lot of times when I do proofs, I don't bother to switch to a K, not because I'm trying to be unclear. Let me move Professor Ron over. I'm just trying to say that if you want to switch, that's fine. If that helps for clarification, and I think that's what Dr. Stewart is doing. So you're thinking, I need to show that if I add the next counting number, I can actually get this formula true for K plus 1. And I want to make sure that I get it legitimately by using this. So this is what we call the induction hypothesis. Hypothesis. So now we just say, okay, well, let's add the first k plus 1. So I equals 1 to k plus 1. So we can say then, well, let's write out what this means. Well, we need to use this, but this is just adding 1 basically to this sum. So we can write it in 2 pieces. That is, why not just go ahead and just write out I equals 1 to k plus the k plus 1 term. So for instance, if we ignore the k plus 1 and just sum the k, then we have to write out the term here, which is k plus 1. So when we look at this particular sum, we can just sum the first k natural numbers and then add the k plus 1 natural number. So these are equivalent. Now, why would we do that? Well, the idea is that we want to use this formula because we know if we add the first k integers that the sum equals this, because we assume that. That's the induction hypothesis. So now, and if you like, you can write induction hypothesis. You don't have to, but I'll just say this. If you don't use this, then we didn't do an induction proof. So now the induction hypothesis says that this sum is just k times k plus 1 divided by 2 plus k plus 1. So do we get our formula where n has been replaced with k plus 1? That's what we have to show. Now you can't just walk up to the formula and replace n with k plus 1 and say, okay, I'm done, I proved it by induction. No, you have to get that formula by using the induction hypothesis. So now what we can do is get a common denominator. So we can see k plus 1 over 2 plus 2 times k plus 1 over 2. So just get a common denominator. Now we can factor. So we have a k plus 1 divided by 2. And what's left over? Well, notice here, when we look at this, we've got a k here that we didn't factor. And here we have a what? We've got the copy of 2 or k plus 1 here. So notice we factored this, but we left the 2 out. So plus 2. Now when we look at this, again, multiply back through, we get k times k plus 1 over 2. And then we get 2 times k plus 1 over 2. So this is good. So now let's rig it. That looks exactly like what we need. So now we have what? K plus 1. So we write this in a creative way. And then we write k plus 2, if you like, as k plus 1. Even though the k plus 2 does what we need, we just write it in a way that looks like we replaced n with k plus 1. Now this is extra here because this is doing what we need. Because when you look up here and say, okay, well, n has been replaced with k plus 1 here, and it looks like it's been done here because k plus 2 is really k plus 1 plus 1. So what I did at this point is to see where you can match things up. Notice the n here is replaced with k plus 1. And the n plus 1 is replaced with what? Again, k plus 1 plus 1. So this is really our formula with n replaced with k plus 1. So if we add the first k plus 1 integers, we get a valid formula. That is where n is replaced with k plus 1. So this implies that P of k plus 1 is true. I mean, you think about it, we assumed it's true if we add the first K counting numbers. And then if we want to add an additional one, is this still true? Well, it certainly is. So we were thinking, okay, I see what you're saying now, Professor Ron. This K is arbitrary. That's why we say for some K. So we're not saying a specific K, we're not fixing K, we're just saying in the sense that, okay, here's an abstract K. We're not gonna say, okay, it's exactly this number. We're dealing in the abstract. And so we verify if it's true, the logical statement's true for K, we now have verified that it's true for the next counting number. So we have shown 1 and we've shown 2. Therefore, P of n is true for all n. That is, S, which is this, is actually all natural numbers. So by induction, and this is where you can just be cheap. You don't have to write this out, just call it P of n. P of n is true for all natural numbers. So the idea here is the first time you see this, you're thinking, wow, it seems like, okay, well, it's not like I normally prove things, Professor Ron. I usually think about doing a derivation because that's really been the method that we've used. But I don't want you to think that derivations are not the way we normally go with mathematics. We do a combination of both. The nice thing about the induction process is that it is valid for the natural numbers. And so now what you can see is that when we actually do the induction process, we accomplish 2 things. Now, you might be thinking, what does this mean for working with numbers in general? Let's do another example. So how do you get better at induction? You just do examples. And I will say this, I want you to be familiar with the process. And just remember, with each induction step, the part 2, every problem will present something new. And so you have to be open to the fact that, okay, I got to use this somewhere. I've got to use the induction hypothesis. And that's where you have to sometimes apply creativity like you do in solving trig equations. We know trig equations can be difficult. So it's the same thing here. We have to say, well, let me look at it this way to push things forward. So let's look at an example. Another one. We've got several here. Now, I pulled this from the WebAssign. This is a nice simple example called the, and we'll do some more, let me just say this, we'll do some more of the counting number type proofs that we've already used, the famous formulas I've already talked about. We'll do some more of those just to make you feel a little bit more comfortable. But let's do an example here where we talk about the Fibonacci sequence. This is a very famous sequence in number theory that volumes have been written on the Fibonacci sequence. And so you could spend a lot of time studying this. And so this is just the tip of the iceberg. So what we want to do is, let me describe what the Fibonacci sequence is. That is, we will assume in the WebAssign uses the F1, F2, etc. for the elements of the Fibonacci, F for Fibonacci. The first element is going to be 1, and the second element is also going to be 1. And then, this is what we call recursive. For all other Fibonacci, we'll say the nth Fibonacci will be the sum of the previous 2. So this will be F, excuse me, n minus 2 plus F n minus 1. And this will be for n greater than or equal to 2. So the Fibonacci sequence is defined recursively. So this is recursive definition. So when we think of Fibonacci, we can just start writing down some of the elements. So, excuse me, we'll add the previous two, that'll be 2. Now to get to the fourth one, we add 1 and 2, and we get 3. To get to the fifth one, we add 2 and 3, and get 5. And to the sixth one, we add 3 and 5, and we get 8, etc. So the like I say, if you look into the Fibonacci, you can keep yourself busy for many days studying all these interesting properties. So what WebAssign does is it's a very interesting logical statement. So here's our logical statement. If we add, and I'm doing this because it's similar to the last problem, if we add the first n Fibonacci numbers, so I equal 1 to n of the Fibonacci numbers, what's this going to be? Well, the proof looks like this. This is going to be the n plus 2 Fibonacci number minus 1. And this will be for n greater than or equal to 1. So that's our logical statement about natural numbers. So if we look at this and we say the third, that's 2. We look at this and think of what we have here, and we subtract 1. So if we, well, let me not even talk about it. Let's just see, does this even make sense? Again, did Professor Ron make this up? Let me not just talk in circles. Let's just go ahead and see if this makes any sense. So basically what we're saying is that if we sum the first n Fibonacci numbers, then that will just be the n plus second Fibonacci number minus 1. So let's check 1. Let me not just talk, like I say, in generalities. Let's just check this out. So we want to do an induction proof. And we will need to use our definition. This tells us about the Fibonacci sequence. So number 1, let n equal 1. Okay, well, let's do it. Just like the last one, we have I equals 1 to 1 of fi. Well, we start with 1 and end with 1. So this is f1. And so now f1 is 1 and question mark. Now this says we replace n with 1. So this will be f3 minus 1. Well, f3 is 2. That's why I wrote out several of these. This is 2 minus 1, which is 1. Okay, well, that looks good. That is true. So this implies P of 1 true. Now, I was trying to do this by just kind of marching around the numbers, and I'm like, well, no, let's not do that. Let's just go ahead and see, is there any reason to even look at this? Well, we can see for n equal 1, it is true. And like I say, the mathematician was checking this out and noticed a pattern. You know, this is a pattern. I believe it's true. I really do believe it's true. Let's do an induction proof. So this n equal 1 true, we have a reason now to move to step 2. So let's do it. Now, step 2 can involve college algebra. It can involve all kinds of things. The step 2 is what keeps everybody busy. So for 2, for some k in the natural numbers, P of k is true. So now we're going to delve into the abstract. And of course, we want to use the P of k being true to show that P of k plus 1 is true. So now what does this mean? Well, this is just like the last one. Again, this is why I'm doing this. We can say that the sum of the first k Fibonacci numbers, and notice I'm using the summation notation. I think in the WebAssign they write it out, but I want you to use your summation notation to get used to it. If you never use it, you're never going to feel comfortable with it. And it is very powerful. The summation notation is very powerful for writing plenty of information without having to fill up the page all the time. So now this is going to be our formula. That is f k plus 2 minus 1. Again, switching to k is your choice. The WebAssign does it, and it's fairly standard, but if you want to stick with n, that's fine, but the WebAssign uses the k just for clarity. So when we look at this, this is our induction hypothesis. Induction hypothesis. So now we just want to say, again, let's look at then, or consider, if we look at the sum of the first k plus 1 Fibonacci, I equals 1 to k plus 1. So we're going to use the same technique. So we look at this and say, okay, well, we're going to break this up into two pieces. We're going to sum the first k so we can use the induction hypothesis. This is where the summation notation is very valuable. And now, of course, the I here is replaced with k plus 1. K plus 1 Fibonacci. Now, if we look at this, we're thinking, okay, well, we can use induction hypothesis on this. We know that the sum of the first k is actually this formula. So this is f of k plus 2 minus 1. And then we have plus f of k plus 1. Now, when you look at this and you think about what we're doing in this sense, notice these define Fibonacci. And so what we want to be able to do is to replace the k with k plus 1. So now let's put these together and use the definition. So put these two items together, and we're going to think about the definition of the Fibonacci sequence. So we have f k plus 1 plus f k plus 3, excuse me, k plus 2. I'm thinking ahead. Now, when you look at this and we go up here and we think of these as being the previous two, so to speak. So we know that we can get the next Fibonacci number by adding the previous two. So this would be f sub k plus 3. That is, the previous two elements here, k plus 1 plus k plus 2, will give us the next Fibonacci. So this will equal, by definition. So now, of course, here, this is what? Induction hypothesis and definition of the Fibonacci sequence. This will be f of k plus 3. But we want to make it look like that. So this will be f k plus 1 plus 2. Now, again, this is fine here, but when we look at this, we have our formula basically where n has been replaced with k plus 1. So we have k plus 1 plus 2 minus 1. So what we're seeing is if we add the first k plus 1 Fibonacci numbers, then we get the f sub k plus 1 plus 2 minus 1. That is, we get our formula where n has been replaced with k plus 1 using what? The induction hypothesis that we have here. And then combining these two and using the definition of the Fibonacci sequence. So This is not as difficult as the previous one algebraically, but it does require that we use the definition of the Fibonacci sequence. So this step right here just kind of makes an effort to make the process a little bit more clear, because the goal is to produce a formula here in the induction step where n has been replaced with k plus 1. And we see that we have this. This is exactly what we need. N replaced with k plus 1. N replaced with k plus 1. And I say replaced with k plus 1 legitimately, not where you just went up there and replaced n with k plus 1. You have to do that by utilizing the process of induction, which means using the induction hypothesis. So this implies P of k plus 1 is true. So by induction, P of n is true for all natural numbers. Now, the thing is that often, you know, you think about number theoretic arguments and things of this nature. Induction's not necessarily something you use all the time, but when you're working with sequences and the like, which are natural logical statements about natural numbers, it's very useful. So induction is not going to be something you use every time you open a math book. If you're in a discrete math class, you'll use it more, of course. If you're in a computer science class, sure. So again, look at induction as a method of understanding abstraction, where we actually verify formulas or logical statements about natural numbers as a means of adding a new technique to the toolbox, so to speak. Okay, so let's look at some more examples. Now, when it comes to utilizing what we call the summation notation, that's really effective. Sums are just nice in the sense that we can manipulate things more efficiently and write things in a way that easy to assess. So let's look at an example, and here's another one from your web assignment. I've got several here, where we have an inequality. So here's an example. Here's our P of n. So our logical statement says the following. It says that 100n is less than or equal to n cubed. And I like this problem because we don't start with 1. We have n greater than or equal to, in this case, 1,000. Excuse me, 10. Well, 10 cubed is 1,000. So when we look at this, you can think about all the ones we've done so far, but there's no sum here. This is an inequality about natural numbers. And you're thinking, okay, 100n, we're thinking, all right, so this will take the place of the 1 to 10. So we want to see if it's true for 10, and then apply the step 2 to see if we can push this out for all natural numbers 10 and greater. So the idea is that you're thinking, well, what if we were doing a proof about real numbers? You're thinking, oh, well, we could solve an inequality, Professor Ron. That would work. We could solve an inequality. And you're thinking, okay, and then if you solve the real inequality, you could work backwards to the natural numbers. So if it's good for all the real numbers, it would certainly include the natural numbers. So you could actually prove this by college algebra methods. But as an inductive proof, this is a really, really good example. So as you'll learn in Calculus 2, when you have certain properties about real limits, you can always restrict to the natural numbers to get the same property for sequences. So that'll be a very valuable technique. So when you look at this, what comes to mind is I could prove this using inequalities from college algebra. But Professor Ron wants us to do this by induction. So again, when you're proving something in a class, you choose whatever method you like. But since I'm trying to teach you about induction, I want us to think inductively. So let's just say this: prove by induction. But when you were driving the car, so to speak, you can take any route you want, as long as WebAssign didn't format it in a certain way. That's kind of humor, but you see what I'm saying. If you're in control, you do it the way you want. But I do want you to know how to do induction. So let's do our proof by induction. Now, of course, every time we do a proof, we could really write the word proof, but I just write the one for the steps. So anytime we're doing this, we're actually doing a proof. So if you want to write that, you can. I just don't want to make you feel like, you know, we've jumped into the abstract realm and we're sinking. I want you to think of it in terms of two steps. So let's start with n equal 10. And so we'll say 100. Well, let me not add too many zeros. So we're going to start with P of n, where n is equal to 10. So we have 100 times 10. That equals 1,000. And we know that in this particular case, that 1,000 is less than or equal to itself. But that is equal to 10 cubed. So even though this is very simple, certainly a number is always less than or equal to itself, but 10 raised to the third power is 1,000. So it is true that what? 100 times n is less than n cubed when n equals 10. So, I mean, kind of obvious, but true. So now you're seeing why we have to start with 10 and not 4 or 5, because it wouldn't be true. So this implies P of 10 is true. So this is the case where we don't start with 1. So you don't always have to start with 1. Maybe you start with 2, maybe you start with 5. In this case, we start with 10. So this at least is giving us a reason to move to what? Step 2, which is this. So now, for K, we're going to get to use the binomial theorem. So I keep squeezing in the binomial theorem before we do it formally, just to get you ready for it. K, some natural number. P of K is true, or P of K true. And what does this mean? This means that 100K is less than or equal to K cubed. Now, of course, here, remember, K is at least 10. So we can't, you know, we need to keep that in mind. So we know where K starts, or it's got to be a number that's 10 or bigger. So this is true. This is our induction hypothesis. Now, when you look at this, we want to think binomial theorem. So I'm gonna do a little work here. So I'm gonna say in this case, consider the following. That is 100 times K plus 1. So we're assuming this is true, and then we have to replace K or N with K plus 1. So we start with 100 times K plus 1. Is that actually less than or equal to K plus 1 cubed? That's what we have to show. So when we look at this, we're thinking, okay, what does this equal? Well, this equals 100K plus 100. Now, when you start your induction proof, you're thinking, well, I'm going to start this way, but I'm not sure if this is going to give me anything. Maybe I'm going to have to adjust some things. But if I start here replacing n with k plus 1, I get this. And then I'm thinking, okay, I do know that 100k is less than or equal to k cubed. And the goal is k plus 1 cubed. So we think over to the side that this is really what we need. We need 100 k plus 1 less than or equal to k plus 1 cubed. We gotta be able to produce that inequality. That would be the induction step. So now we're thinking, okay, well, we've got what? K cubed plus 100. Now this is where the process is actually very simple. We can always add positive numbers to this right-hand side and make it bigger. Now, this is where we use the formula for the cube that we've used many times. Notice, and this is another prelude to what we're going to be doing. This actually equals what? K cubed, remember, we've done this many times, plus 3k squared plus 3k plus a 1. So when we look at that, just doing the expansion here, remember we did the a plus b cubed when we were doing the sine cubed, or the sine to the 6th power with the reduction formulas. So what we're going to do here is think, well, we've got, in this particular case, we've got a 100 here, and we know k is at least 10. So if we did 3 times k squared, that would be at least 300, okay? So that's going to take care of that. So we could say this is less than or equal to k cubed plus 3k squared plus 3k. So when you look at these two terms where k is greater than or equal to 100, that's going to be at least 300, and that's going to be at least 30. So that's bigger than this. So we can now say this is truly bigger than this, and then just add the 1. So again, what we're doing at this point here, let's write it in. This is induction hypothesis, and this is binomial theorem, at least the part that we know, and k is greater than or equal to 10. So that's the creative part I'm talking about. You're thinking, well, I'll just do the inequality, Professor Ron, that I can do the BV technique. Well, here's the thing. I want you to think about this inductively. And so now when you look at this, you're thinking, all right, well, that's just k plus 1 to the 3rd power, using our formula from the very first week of class. Remember we had a plus b. That was the very first week. I said we will use this before we get to the actual binomial theorem. This is a cubed plus 3a squared b plus 3ab squared plus b cubed. And we've used that several times in the course. And so what we're seeing here is when it comes to doing induction, we may have to utilize an identity from our past. And so now we're thinking, all right, well, let's just see what we have here. We have 100 times k plus 1 is actually less than or equal to k plus 1 cubed. That is, n has been replaced with k plus 1 using the induction hypothesis and our mathematical knowledge. So we did use the induction hypothesis. So now we say n replaced with k plus 1. you always give yourself a fighting chance, ladies and gentlemen. You think, what's the goal? I need to produce that. That is, we did produce that right here. So this implies that P of K plus 1 is true. So now we worked it for 10, replaced 1 with 10 because that's the first one for which it worked. And then we assumed P of K and showed that that meant that P, or implied that P of K plus 1 is true. So we did 1 and 2. So now by induction, P of N is true for all N element of the natural numbers. So like I say, when you get to infinite series and you're working with sequences and things, you'll use real results to restrict to the natural numbers to get a way to get free limits for sequences. So there are many ways to prove things. Induction's not the only way, but it's a very convenient choice when you're working with just natural numbers. So look at this and just say, okay, I've got other methods available to me, Professor Ron, but I see that if I use my knowledge of certain identities, I use my knowledge of the induction principle, mathematical induction principle, then I can actually work this out. So again, when it comes to verification, so to speak, when you've got logical statements about natural numbers, this is a very, very tried and true technique. You see it in any book on algebra, any book in number theory, any book in combinatorics. It's a very, very powerful technique. And again, sometimes simple, sometimes challenging. It just really depends on what you're working on. And we see with each problem, we might have a little bit different technique that we have to apply. Okay, so what I wanted you to do is look at another example. Again, you can try the, if we have time, we may work on one of the other famous formulas. But I wanted to do an example that came straight from the geometric. Because when you think about the geometric, we consider the fact that we actually proved this with partial sums. So here's another example, and this is good practice. So here's our P of N. So you're thinking you could start with Professor Ron's partial sum formula and prove that by induction. Remember, we proved it algebraically, but you could take my formula and do a proof by induction. That is, you already, maybe you were working with the algebra and you say, I want to verify this by induction. Well, here's an example that is geometric. So we have I equals 1 to n plus 1, in this case, of 2 to the I minus 1. This is, and I'm going to give you a formula. Well, let's just write out what this is. I'll give you the formula, but we're going to do this by induction, not using the partial sum formula. So when I is equal to 1, we just get 2 to the 0. So we're going to get 1 plus 2 plus 2 squared plus 2 cubed. And now instead of ending with 2 to the n minus 1, we have the upper limit is n plus 1. So we get n plus 1 minus 1, which is n. So what the formula says is that this is 2 to the n plus 1 minus 1. And that should not be surprising if you think about our partial sum formula. So this is a formula about natural numbers. And so here we could just say n, excuse me, is greater than or equal to 1. Now, what we want to do in this particular case is verify by induction. Now, this is a logical statement about natural numbers. And so let's do a proof by induction. So you can write proof if you want. So number one, we'll let n equal 1. So let's see if this is actually true for an initial value of the natural numbers, like we did 10 for the last one. If there's any reason to move forward, maybe this is just ridiculous. I don't think you think that, but let's check it. So we have I equals 1. Now, of course, when n is equal to 1, we get 1 plus 1. So that will be a 2. And then we have 2 to the I minus 1. Now, when we look at this, we can just go ahead and say, okay, well, let's just go ahead and write this out. So we have I equal 1. So that's going to be 2 to the 0. And then I equal 2. That'll be 2 to the 1. 2 minus 1 is 1. So this equals 1 plus 2, which is 3. And then we say question mark. Well, would this be equal to this formula where n is replaced with 1? So we get 2 to the 1 plus 1 minus 1. So that's 2 to the 2 minus 1, which equals 4 minus 1, which is 3. Now, of course, I spread this out and did all the computation just to verify that we don't, it's better to be meticulous. When you're doing quick algebra, you skip steps and you don't worry, but just kind of work this out where you don't skip any step and you just verify everything and say, oh, okay, good. If I sum here, I get 3. If I use my formula, I get 3. So for n equal 1, this is valid. So check. P of 1, true. So now, step 2. For k, a natural number, we're going to assume that P of k is true. Now, again, I like to work this out because I've asked you to work with a lot of sums in this class, and I don't want you to be afraid of sums. Sums are important in calculus. So I take every opportunity to write them out with the sum notation. So what does this mean? Well, just replace the n with the k. I equals 1 to k plus 1, 2 to the I minus 1. This equals 2 to the k plus 1 minus 1. So basically, we just want to be able to replace k with k plus 1 and get that by using this, which is the induction hypothesis. So now when we look at this, we're good to go. So we're going to think, all right, well, let's just look at the next one. So we'll say then or consider the sum to k plus 2, add one more. So now you're seeing this is a very useful technique with the sums. And we'll use this when we prove the binomial theorem by induction. So now, again, we're going to use the same trick we used before. Let's break it up into 2 pieces. K plus 1, because that's going to be covered by the induction hypothesis. So we're doing this very differently from how we did with the geometric. Plus, now, of course, when k is equal, or I is equal to k plus 2, we get k plus 2 minus 1, which is 2 to the k plus 1. And now, if we look here, induction hypothesis. So this sum here can be replaced with 2 to the k plus 1 minus 1. So we get 2 to the k plus 1 minus 1 plus 2 to the k plus 1. And then, of course, we get to just use laws of exponents. So now this equals, so we get 2 copies of this. So we have 2 times 2 to the k plus 1 minus 1. So just put a 1 there if you like. So add the powers, the exponents. So this gives us 2 to the k plus 1 plus 1. I'll just write it that way where we add them formally. So that's really k plus 2, but notice this is just our formula where n has been replaced with k plus 1. So write this down. N replaced with k plus 1. So now you're looking, boy, this is really different, Professor Ron. We didn't manipulate sums and multiply by r, or with the r here is 2. We didn't do all that telescoping series like you did. That's completely different from this. So basically here, we come up with a formula that we want to show that's true in general for all natural numbers. So once we've used the induction hypothesis here, this implies that P of k plus 1 is true. So I keep going back to this because it's what we're doing. We've shown both of these, so now we get all n. So by induction, P of n is true for all natural numbers. But of course, if you look at this, this is exactly the geometric progression. But notice here, we're going up to n plus 1. So if you use the actual progression, this gets bumped up 1. We know that. And so this would be the formula that we would utilize that we derived last time. So for instance, I'll just say you don't have any trouble with this. We've gone through the induction process several times, and we see this is a valid rendering of this proof. This formula is valid. And of course, it's even more interesting to think of this in terms of how we did it before. So let me just allude to that. So if we look at this, I equals 1. Notice it looks just like what we had before. 2 to the I minus 1. But notice here, in this particular case, we end with the 2 to the n term, not 2 to the n minus 1. So if you like, we can write this way. This will be, let's break it up. Plus, and now of course, when we had the n plus 2 term, that's just plus 2 to the n. This is the formula that we used with the geometric partial sum. So in this case, if you just want to do this or cheat like I did it there, replace n with n plus 1 to get that, this would be A equals 1, R equals, 2. So this would give us, in this particular case, 1, well, A is 1, so we get 1 minus 2 to the n divided by 1 minus 2 plus 2 to the n. So we're getting something like this. So now when we look at this and we think about this, this is just a -1, so this flips around. So this is 2 to the n minus 1 plus 2 to the n. So this is 2 times 2 to the n minus 1. But of course, this is just 2 to the n plus 1 minus 1. So if we just basically used the geometric partial sum formula that I derived last week, we still get the same answer. So that is still valid. This would be another way of doing this, but it wouldn't be an induction proof. So that's what I'm trying to point out to you. Often I don't always take the opportunity to say, okay, well, if we did this the other way, how would we do it? Okay, so So if you're working on a proof or you're doing an example and you see this, you're thinking, well, I'm just going to knock this out with the partial sum formula for the geometric sum and be done with it. Now, if the actual test required an induction proof, then you would have to do it this way. And then you'd think, okay, well, that's fine. Induction is good. Induction is really good when you don't have any other options. For instance, if you've got to show something and you don't have a formula in your back pocket and you're like, well, what am I going to do? I know induction, so you push it through. But remember, induction is more of a formality in the sense that it verifies the logic of your problem and it fills in the details. And it also offers you a formula if it's necessary. So you may have a formula that's come up in your problem and you need to use a particular convergence test and you first got to verify that, for instance, you have a certain inequality that's valid for all natural numbers. And without it, you can't move forward. So you might have to do a quick induction proof. Or you may say, well, I'm just going to do a quick algebraic proof and be done with it. So again, induction is not something you have to do. It's just a new technique. So you can look here and see we use the partial sum formula for geometric series to get the same result. Here, we start with the basic result and we verify it with induction. So you see the interplay between the two, similar algebra, but two distinct methods. Okay, so that's important. It's important to understand that mathematics can be solved in many different ways, and we can see the validity of the induction proof as well as the validity of the partial sum proof. That is, this gives us a partial sum proof, right? A formula here. This says, okay, this is kind of like going backwards and saying, well, I already know this. I'm going to use a proof I've already done. So some mathematicians might say, well, that's kind of a circular argument. Well, in some cases it may be, but it's like, I already know this. You already know theorems about this. So this is just an alternative path. So just be careful when you're doing any mathematical proof or whatever that you follow what the directions say and do that to get your credit, obviously. So let's look at another example. There's a really nice proof result about de Moivre, which involves trigonometry, which I may do. But I want to look at a couple of examples that are in your WebAssign. One more example. This one has to do with divisibility. And we think about parity, even and odd, if it's a multiple of 2 or if it's not. This is very useful in number theory, in series, and also something that you will want to think about as you continue your math education. So you're thinking that might be a good use of mathematical induction. Divisibility is always good use of mathematical induction when you're talking about natural numbers. So let's look at one. Now, when it comes to the induction proof or the induction step, ladies and gentlemen, your creativity can vary. That is, you may work with a colleague and their proof doesn't look exactly like yours, but the results are the same because you use legitimate techniques. So how you push forward your induction step is up to you. As long as it's valid, it's fine. So let's look at a P of n. That is, we have 3 to the 2n minus 1 is a multiple of 8. Is a multiple of 8 when n is greater than or equal to 1. So basically, we're saying it is divisible by 8. So 3 to the 2n minus 1 excuse me, 3 to the 2n minus the quantity 1, and I won't always have to click inside the box. So this we're purporting for natural numbers is always divisible by 8. That is, it's a multiple of 8. 8 divides it. We can say it 3 or 4 different ways. So we want to do a proof by induction. This is about natural numbers, and you're thinking, well, could I just start checking a bunch of numbers? And you know what, ladies and gentlemen, that might be why you came up with this. You just started checking several cases and you kept getting the same result. And so you're like we are with adding the first in natural numbers. You're like, is this always true? I think it is. So in number theory, induction, and when it comes to divisibility, is very powerful because you just want to put it to rest. So let's do a proof with induction. So now we'll say n equals 1. So is this true for n equal 1? Well, let's test it out. 3 to the 2 times 1 minus 1. Well, that's just 3 to the 2 minus 1. So that's 9 minus 1, which is 8. And of course, 8 is a multiple of 8. It's just 8 times 1. We just say this equals 8 times 1. So that's fine. So this implies that P of 1 is true. So when you look at something like this, you're thinking, I really like the initial step. The initial step is always my friend. So again, by this end of this lecture, if you don't understand induction, then you have been asleep, because I don't think I could make it any more clear than I have. The thing is, ladies and gentlemen, look at this as a new technique, not as the reason for studying STEM. You want to be a STEM professional. Look at this as a technique to broaden your horizons. That's why induction is so valuable. And some of you that go into computer science, you will be taking a number theory class, and you will see this over and over again. And even those of you that go into engineering, you may end up in a number theory class too at U of H or Texas A&M. So now let's do the difficult part, right? So this was the first part here. And then we say, okay, for K, element of the natural numbers, we're going to assume that P of K is true. So what does that mean? That means that 3 to the 2K minus the number 1 is going to be a multiple of 8. So let's write this in an algebraic way that makes sense. We're just going to call this 8 times T, where T is some natural number. So this is where we have to start using some algebra. If this is divisible by 8, then it's a multiple of 8. So it's just 8 times some natural number. That's where the abstraction comes in. All we want to make sure is that when we look to the K plus 1 case, that we result in a multiple of 8, and then we're done. So again, this is our induction hypothesis. So what we want to do with the hypothesis is write it in a way that it's mathematically correct. That is, it's providing the mathematics that we need, that this is written in a way that we can use. We're going to say, this is a multiple of 8. That works in an English class, but we have to write it in terms of mathematical symbols. Okay, so now let's consider, or then, whichever you want to write, consider the next step. That is 3 to the 2K. Well, let me write this where we'll have a 2K plus a 2, but let me write it as 2 times K plus 1. So we want to replace K with K plus 1 and see, again, if it works for this next integer, positive number, or positive integer, so to speak. So when you look at this, you're thinking, okay, well, we want to be able to use this. And so first, what we can do is just say that this is just what? 3 to the 2 times 3 to the 2K minus 1. So if we use the laws of exponents, this is 2K plus a 2. So that's 3 squared times 3 to the 2k. And you're thinking, how am I gonna get this to work? Well, this is where we can use a technique that we've used a million times in the previous lecture. We like to multiply and divide by the same thing, or we like if we're completing the square, what do? We add and subtract the same term. If you say you've never done that, then that's a fib, because you've been doing that ever since you've completed the square. It's like the student says, I don't need theory to do mathematics. That is a complete and utter nonsense. Without theory, you can't do anything in mathematics. And we use it all the time. So now we're thinking, somehow I've got to get this into the mix. So I've got a 9 here. We love 9s because when we subtract 1 from them, we get an 8. That's a good thing. So what we want to do is add and subtract 3 to the 2k. So we can somehow combine it with this -1 to use that 8 times t. So this is the key. It's not always just going to fall out on us. Like when we do the sums, you have to break up the sums so you can see the induction hypothesis. So the key here is to say, all right, well, let's add and subtract the same term. Now, this is not unique, but it certainly does work. So I'm going to write this in red. So I wrote this way so you could see the reason for wanting to do this. And then we can group. So now add and subtract the same term. So essentially we've added 0. So now we can group. So this equals this. Now notice induction hypothesis right here. Induction hypothesis. See the power of the induction hypothesis with divisibility. Otherwise, you'd just be sitting here checking number after number after number. And ladies and gentlemen, that's not a proof. That's good work, but it doesn't get you to the finish line. So now, okay, well, first here, we can factor the 3 to the 2k. Now, of course, here, that's the induction hypothesis. That's just the multiple of 8 times 2. So here we say induction hypothesis. So, like I said before, there's that 8 again. That is, we get what? This just equals 8. So this equals 8. So we have 8 times 3 to the 2k plus 8 times t. Now, of course, 3 to the 2k and t are both natural numbers, and we can factor the 8. But now what we see is that we have 8 times a natural number. That means that this is a multiple of 8. By definition, 3 to the 2 times k plus 1 minus 1 is actually a multiple of 8. So write this, a multiple of 8. So we're done in the sense, at least, that we have shown that if we consider the next natural number here, we still get a multiple of 8 if we assume that the result for k was a multiple of 8. So this implies, now you could just call that alpha if you wanted, which is a natural number, but that's done. This is a natural number, element of the natural numbers. So this implies p of k plus 1 is true. So by induction, P of n is true for all n element of the natural numbers. Don't get me wrong, ladies and gentlemen. Of course, this is new, but the steps should be very clear to everyone. The idea here is that now it's like, we're filling in gaps. When you get to calculus, you're going to fill in so many gaps that we've created in our pre-calculus courses. So we can see here where the induction is even more powerful than in the previous example. We didn't have anything to work with here except induction. You can look at this algebraically and think, oh, well, look what we did here. Could I morph this into an algebraic proof? Well, the idea is that if we test this enough, and then we say, you know, I think I have a result here. The induction procedure verifies it completely, and then you're done with it. And so if you need to use this expression anywhere in your work, you indeed know for n greater than or equal to 1 that this is a multiple of 8. And then you can see the power of number theory with huge numbers and prime numbers, how in computer science, number theory has become the linchpin of why we can do anything with cryptography, why our accounts online are safe. So a lot of you computer science people may be working one day in a STEM career where you program for a major bank, Bank of America or BB&T, keeping their accounts safe and changing the code all the time to keep all the criminals from stealing our money. But just remember, the only way we can survive in this technological world is to stay ahead of the people that are trying to do us in. And that's why the STEM professionals are important, okay? We have many talents in our world, but we have to have people like yourselves that will keep everything running. We've got to have engineers, we have to have mathematicians, we have to have computer scientists, we have to have doctors, nurses, we have to have people in STEM to keep our society moving. And so we can enjoy all the other things that we take for granted, like we've seen with this COVID pandemic. So again, just remember that you have a very honorable route by staying with the STEM curriculum to be one of the many important people that keep our world functioning. Now, so I'm not saying that induction is the linchpin of our existence, but it's certainly a very enjoyable and important technique. Now, to close, I just want to say a couple of things about even and odd. There are several examples here. When you think about parity, and you might think, well, considering the last example, let's just look at an example here. We'll say P of n. And so we're going to just kind of think outside the box, and I want you to finish this. Say we have n times n plus 7 is a multiple of 2. Is a multiple of 2 for n greater than or equal to 1. So we're thinking, you know, or this is, or n times n plus 7 is divisible by 2. It's even. And so maybe we're thinking about this and we want to do an induction proof. And I want you to finish this, but let's just say we're thinking outside the box. And so for instance, say n was an even number. We can write any natural number that's even as 2 times a natural number. That's the definition of even. It's a multiple of 2. So then we're thinking, okay, if that's true, what are we going to get? We're going to get what? 2k, and then we have 2k plus 7. So now if you look at this, this is just 2 times k times 2k plus 7. So we're just being creative with the algebra. So 2k and 2k plus 7. So if n is already even, this is a multiple of 2 because again, this is a natural number. So this is a multiple of 2. Multiple of 2. Okay. And now what if n, what's the only other case? 2k plus 1, like we do in trigonometry, the odd multiples of pi over 2 or something. So we'll say, okay, well, we get 2k plus 1, and then we get 2k plus 1 plus 7. So this is what, 2k plus 1. And then, of course, this is 2k plus 8 if we add the 1 and 7. But so this is now 2 times what? K plus 4 times 2k plus 1. This is a natural number. This is a multiple of 2. Multiple of 2. So it looks algebraically that, yeah, this is always divisible by 2. So here's what I want you to do. Or it's like, well, Professor Ron just said, well, what if n is even? You get an even number. If n is odd, n times n plus 7 is also even, okay? So now what I want you to do, and try this, prove this by induction. Prove this result by induction. That is, algebraically, this is good. But now we want to think that we didn't do this, or we thought about this, and we want to just put that last nail in the coffin and say, boom, this is true for all natural numbers. So here's what I want you to do. Prove by induction. So what I want you to do is start with 1, and then assume P of K true, and show that that implies P of K plus 1 is true. So again, this might be how you come up with your P of N. And this is fairly convincing here. We're thinking, yeah, this is even. We're convinced of this. So now do the same result by induction, okay? So what are we going to do with this? Well, the binomial theorem that we work with next class will be for the natural numbers. It will not be the generalized version for real exponents. It'll be for, like, you know, we've already done 2 and 3, 4, 5, 6, things like that. And so that will be a logical statement about natural numbers if we actually write a formula. And so the formula will have to be what? We're thinking, well, can we do a little combinatorial proof of it? Sure. Can we do an induction proof? Sure. And the induction proof will require some algebra about sums and some of the algebra about the terms that multiply. We remember we've got a 1, 2, and a 1 in the square. And for the cube, we have the 1, 3, 3, 1. And we're thinking, where do those numbers come from? Is it just that we collect all the terms and that's what we get? Are those special numbers? Well, it turns out that they're very special. And so we need to talk about that and then just see how we can use induction to move all of this forward. So this, what we've done today, is a nice prelude to that. And then it will allow us to sum up some ideas about the binomial theorem that we've left hanging all term. So I will put up an announcement about the final exam, and then of course Thursday will be the last new stuff, and then we'll have there's a practice final on the practice 1 test that you can work through if you like. The final will be comprehensive, and of course it'll have the new stuff, but everything will pretty much be spread out. It's not like it's going to be 80% new stuff. It'll be spread out, and you'll have representative problems from all of the new things, but not an overabundance of anything. So just remember that I want you to be sure that you get the new stuff and go back and review old tests or quizzes of the old stuff where you feel rusty, okay? If you're comfortable with logarithms, you're not going to see anything new on the final. If you're comfortable with rational zeros theorem and factoring, that's fine. Maybe you want to go back and spend some time on trig equations. Maybe you want to go back and spend a little bit of time on the conic section. Again, focus on things that may be rusty. So a little bit raspy today, but the cold weather I love, so I can put up with it. I appreciate your attendance today. Hopefully that you have found this to be illuminating. Those of you that are going to be computer scientists, induction will be your friend. So if I don't see you at office hours, I look forward to seeing you again on Thursday when we talk about the binomial theorem. So everybody stay warm, and we'll see you then.
Have a good day, sir.
You too. Thanks.